Hey everyone, in this video we will talk about input-output organization. So we'll learn about peripheral devices, we'll learn about input-output interface, and then we'll talk about asynchronous data transfer. Now there are other topics that pertain to input-output organization aside from these, but we'll talk about them in the next video. The input-output subsystem of a device, simply referred to as I/O, provides an efficient mode of communication between the central system and the outside environment. So a computer serves no useful purpose without the ability to receive information from an outside source and to transmit results in a meaningful form. Now, devices that are under the direct control of the CPU are said to be connected online. These devices are designed to read information into or out of memory upon command from the CPU. These input-output devices like keyboards, monitors, printers, auxiliary memory devices like magnetic disks and tapes are also known as peripheral devices. So all input-output devices are also known as peripheral devices. Input-output devices are usually involved in the transfer of alphanumeric information to and from the device and computer. The standard binary code for alphanumeric characters is ASCII. ASCII, as you might recall, we have already discussed in a previous unit. All right, now let's start with input-output interface. Let's see what an I/O interface looks like. So an I/O interface provides a method for transferring information between CPU and internal storage and external devices. Peripheral devices need special communication links to interface them with the CPU. These special links are needed because of the differences that exist between the CPU and peripheral devices. Now, what these differences are important to understand because that's the entire purpose of having a separate input-output interface between the central system, your CPU, the memory, and the peripheral devices. So let's take a look at what these differences are. So the first difference that exists between CPU and peripheral devices is the manner of operation. Peripheral devices are either electromagnetic or electromechanical devices, and their manner of operation is inherently different from that of the CPU and memory, which are both electronic devices. Therefore, signal values need to be converted. All right. So when CPU, memory, and peripheral devices are required to communicate with one another, there has to be one standard way to represent all the signal values, because otherwise electromechanical and electromagnetic devices are inherently incompatible with electronic devices. So that's the first difference, which necessitates the use of a proper I/O interface. The second difference that exists is data transfer rates. So data transfer rates of peripheral devices are usually lower than that of the CPU. So CPU is much faster than any peripheral device, which means a synchronization mechanism is needed. If there has to be some kind of transfer of data between the CPU and any given peripheral device because of the mismatch in data transfer rates, a synchronization mechanism is needed. Again, this is provided by the I/O interface. The third difference that exists between CPU and peripheral devices is data codes and formats. So data codes and formats in peripherals differ from the word format used in CPU and memory. So again, if data needs to be transferred between CPU, memory, and peripherals, there has to be a common ground on which this kind of transfer can take place, and that is provided by the I/O interface. Finally, there are the operating modes. Now, operating modes of different peripherals are different from each other, and each must be controlled so as not to disturb the operation of other peripherals. So not only are peripheral devices inherently different from CPU and memory, but different peripheral devices are also different from one another. They also operate differently. All right. So in order to provide some method of synchronization between these peripheral devices, so that the operation of one of the devices does not impact the operation of any other peripheral device, some kind of interface is needed. Again, this interface is your I/O interface. So this is in a very simple block diagram format. This is what this interface does. So we have the processor, your CPU. As you already know, there are data lines, address lines, and control lines, right, that emerge from the CPU, and meet the memory and the peripheral devices. Now, each of your peripheral device, here for instance, we have taken the keyboard, the display terminal, the printer, magnetic disk, any other peripheral device that your system could have. All of them are connected to these three buses through an interface. And this is the interface that actually allows your processor and the memory to be interoperable with the peripheral devices. These are the interfaces that actually take care of all the differences that we just discussed between the inherent operation of the processor and the memory, and allow for a seamless communication between the different components of a computer system. All right, now let's talk about asynchronous data transfer. The internal operations in a digital system are synchronized by means of clock pulses. These clock pulses are supplied by a common pulse generator. Now, generally, two units, for example, CPU and I/O, are designed independently of each other, right? So, if the registers in the interface share a common clock, the transfer between the two units is said to be synchronous. So although they are designed independently of each other, if the registers in the interface between the CPU and the peripheral device, if the registers share a common clock, then the transfer of the data information between these two units is said to be synchronous. In most cases, however, the internal timing of each unit is independent. And that actually makes more sense because these components are designed independently of one another. They operate in different ways. They generate different electrical pulses. Their data transfer rates are different. So everything about them is different. So it makes sense that they run independent of each other, right? Their internal clocks and their timing signals are not uniform. And then the resulting data transfer that happens when the internal timings of these different units is independent is known as asynchronous. So we are going to talk about asynchronous data transfer in much more detail than synchronous. So in fact, we'll be focusing only on asynchronous data transfer, and that is the only reason for that is this is more common. So this is a more commonly occurring phenomena within computer systems instead of synchronous data transfer. Now, there are two main methods of accomplishing asynchronous data transfer between two or more communicating units. We can have strobe pulses, or we can have a method of handshaking. Strobe pulses are applied by one of the units to indicate to the other unit when the transfer has to occur. And on the other hand, in handshaking, each data item being transferred is accompanied with a control signal that indicates the presence of data on the bus. So the unit receiving the item responds with another control signal to acknowledge the receipt of data. So let's take a bit more detailed look into the method of operation of both strobe pulses and handshaking. So first, strobe control. Now the strobe control method of data transfer employs a single control line to time each transfer. So the strobe may be activated by either the source or the destination unit. This is what a strobe initiated data transfer looks like, and this is what a destination initiated strobe transfer looks like. So what happens here is, say we have two units. This is the source, this is the one who's going to send the data, and this is the destination unit. This is the one that's going to receive the data. All right, so we have a data bus between the source and the destination unit, and we have an additional control line known as the strobe control line. So this is the strobe control line. So how this happens is, suppose this is the data, this is the clock diagram of your of the data that the source unit wants to send to the destination unit. This is 0. With this clock pulse, the data becomes 1. That means from this to this, we have a valid data. So you'll see here, the source unit sends out two signals, the data and the strobe. All right. So the strobe, you'll notice, starts a bit a small time unit after the actual starting of the data. All right, so the data started here and the strobe comes a bit later. This idea of strobe is to indicate to the destination unit that the source unit has sent some data. The source unit has placed some valid data on the data bus. That is the idea of the strobe pulse. All right, so how this happens is, the source wants to send some data to the destination. It places the data, this is the valid data, onto the data bus, and once the valid data is placed onto the data bus, it sends out a strobe signal. The strobe signal starts a bit after the data and it finishes before the actual data finishes, and the idea of the strobe is to just give a nudge to the destination unit, just to indicate to the unit that I'm sending some data your way, right? So this is what the strobe pulse does. What happens in case of the destination initiated strobe transfer? Now again, the source is the one that's going to send the data, the destination is the one that's going to receive the data. But the thing here is, in this case, the destination is the one that initiates the transfer. The destination asks for some data. In this case, the source sends some data to the destination. In this case, the destination asks for some data to be sent. All right. Now, in this case, what's happening is, you can see the data bus is going from the source to the destination. And this is the normal flow of data, right? It is going to go from source to the destination, but the strobe is coming from the destination to the source. This is the only difference between these two methods of operation, right? So the destination indicates to the source unit that it needs some data through its strobe pulse, which is why in this case you can see that the strobe actually starts a bit sooner than the data. This is because first the destination unit sends its strobe signal to the source unit, and when the source unit receives the strobe, only then it places some data onto the data bus. That's why it takes a bit of time, a little bit of time, because first the destination unit indicates to the source unit that it's ready to receive some data with the help of the strobe pulse, and after the reception of the strobe pulse, the source unit places some valid data onto the data bus. So this is how source initiated and destination initiated strobe pulses work. Now the second method for data transfer was handshaking. So now see, in the strobe control method of data transfer, the source unit that initiates the data transfer has no way of knowing whether the destination unit actually received the data item that was placed on the bus. And you can appreciate this from these diagrams itself, right? So the source unit that has initiated the data transfer has no way whatsoever of knowing whether the destination unit actually received the data item. Similarly, if the destination unit initiates the data transfer, it has no way of knowing whether the source unit has actually placed the data item on the bus. Because in this case, in source initiated, what's happening is the source unit places the data on the bus and it places the strobe. And that is it. That is all the source unit does. It doesn't know if the destination has actually received the data that it placed on the data bus. And in case of destination initiated method of transfer, when the destination unit sends a strobe pulse to the source unit, it has no way of knowing whether the source unit has actually received its notice, whether the source unit has actually received the message. When the data actually gets placed on the bus and the destination unit receives that data, only then this unit comes to know that yes, my signal was actually received. Before that, if the transfer hasn't occurred, in that time period, the destination unit has no way of knowing if the strobe was actually received by the source unit. All right, and this is disadvantageous because in order to allow seamless communication between the sender and the receiver, there has to be a foolproof method of acknowledgements. There has to be a way of knowing whether the other unit is actually receiving your data or whether the other unit has received the strobe pulse. All right, now this problem is solved by the handshaking method. So the handshaking method solves this problem by introducing a second control signal that provides a reply to the unit that initiates the transfer. A reply to the unit that initiates the transfer. So this is what, again, in handshaking also we have source initiated transfer and we have destination initiated transfer. This is the diagrammatical representation of source initiated transfer using the handshaking mechanism. So in the block diagram form, let's see what's happening. This is a source unit, this is the destination unit. The data bus goes from source to destination. This is pretty standard. The data valid line, there is an additional line to indicate that the data is valid, right? And then the destination unit, which is the one who's receiving the data, is sending an acknowledgement back to the source unit that yes, I have received the data that you placed on the data bus. So in case you can actually visualize this using timing diagrams as well, right? This is the data bus, this is the data valid line, and this is the acceptance line that comes from the destination unit and goes all the way to the source unit. This is an acknowledgement that the data has been received. And this is what happens in a source initiated handshaking data transfer. So the source unit, it places the data on the bus, it enables the data valid line. On the destination unit side, what's happening is the destination unit accepts the data from the bus and it enables the data accepted line, right? The source unit, when it receives the message, it receives the acknowledgement, it disables the data valid line and then it invalidates the data on the bus. All right. And then when destination unit sees what source unit has done, it disables the data accepted line and then it is ready to accept more data. So it goes back into its initial state and then the transfer can continue again. A similar thing happens in case of destination initiated transfer using the handshaking protocol. So what's happening in this case is the first thing that happens is the destination unit indicates to the source unit that it's ready to receive the data because this is destination initiated, right? So the destination has to initiate the process. So the first signal that interchanges between the two units is this one, ready to for data. That is, the destination unit is indicating to the source unit that it is ready to receive the data. When the source unit receives this message, it puts the data on the data bus and it enables the data valid line. And this you can actually understand from this sequence of events as well. So the rest of the stuff remains the same. The only difference is who initiates the transfer. The data will go from the source unit to the destination unit, but the initiator is different in each case. And this is how handshaking works. Now, the handshaking method provides a high degree of flexibility, naturally, and reliability because there is a proper acknowledgement protocol in place, right? Because the successful completion of a data transfer relies on active participation of both units. Both units are now involved in the transfer of data. So, the sender is being acknowledged by the destination is being acknowledged by the sender. So, it's a foolproof process. Now, if one of the units is faulty, the data transfer will not be completed. And such an error is detected via a timeout mechanism. So a timeout mechanism is important. Otherwise, both units will wait forever. They will wait indefinitely. If a sender is sending some data to the receiver and the receiver is faulty for some reason, right? So if it's unable to receive the data. So there has to be a timeout mechanism in place. If the data transfer is not complete within the allocated time period, then there should be a mechanism to just stop this entire process and start again, right? So there's an alarm that is produced if the data transfer is not complete within a predetermined time. Otherwise, the units will be waiting indefinitely. So that's it for this video. Just a quick recap. In this video, we talked about input-output organization. So the discussion started with a brief discussion about input-output devices, or otherwise known as peripheral devices, and we talked about the input-output interface. We saw what an I/O interface actually does, the purpose of an I/O interface within a computer system, and then we talked about asynchronous data transfer. In the next video, we are going to talk about the rest of the topics that pertain to input-output organization. We'll be talking about serial versus parallel data transfer. We'll talk about different modes of data transfer. And finally, we'll discuss the input-output processor.